So let's get this train rolling. My name is Marc. Welcome all to this developer workshop on the new columnar table backend, which was briefly hinted at yesterday by Bernd Wiswedel, our CTO, in the What's New session of the Knime Summit. Today, this is more of an in-depth session for developers and for everybody, basically for node developers who are interested in this, and for everybody else who's interested in performance and the nitty-gritty details of optimization. Yeah, my name is Marc. I'm a software developer at Knime. I've been working at Knime for a little over 2 years, and I'm mostly working on performance topics whenever possible. So without further ado, let's get started. The subtitle of this talk is called Fast Tables, and we call these fast tables internally because they make things faster. And performance and making our Knime backend fast is really what triggered this mostly. And what is this new columnar table backend? It is a complete rewrite of Knime's internal table storage backend. And it will be released in labs with Knime Analytics Platform 4.3. So, and this release is planned for December 6th. So the release is just around the corner. Just to start with a bang, this is one preliminary benchmark of this new columnar table backend. I have a workflow here with some frequently used nodes. You see a joiner, you see a sorter, group by nodes, column filter nodes, partitioning nodes, all kinds of nodes that you might be using quite often, and you might have noticed that they could be slower, or that they are sometimes slower than you would hope. And in this benchmark, they're just plugged together, processing data from a data generator that generates about 400 columns of 100,000 rows. And with the old table backend, it takes about 2 minutes to execute this. So this is about 400 megabyte of CSV data, if I'm not mistaken. And now if I enable the new table backend, the same workflow executes in roughly 40 seconds. So it's about 3 times as fast. And this is with 2 gigabytes of heap memory for allocated to the JVM in which Knime runs, and 2 gigabytes of off-heap storage allocated to this new table backend. So it's kind of a fair comparison, and I'm really excited that we've got this far. And this is without optimizing the individual nodes for performance, which is still another topic that we're working on. So what do I want to talk about today? This workshop is made of 4 points. The first one is basically an introduction to, what this is, how it compares to the current table backend, how it compares to the Parquet column store that Knime also had as an extension, and so that's that. Then the second point is how did we design this, and what are the benefits of these design decisions that we made? The third topic will be very technical then, which is about the caching architecture. So basically about how we keep data in memory and when we persist to disk, and how you can configure this caching architecture, or these multi-layered cache to best fit your needs and to best suit your machine. And finally, I'll be talking about the new table API that might be especially interesting for node developers, because this changes a little bit how you write your Knime nodes. So without further ado, let's first hop into what this new table backend actually is and how where it fits into the software stack. So first of all, a little history lesson. Way back, about 3 years back in Knime 3.5 and earlier, all tables that were sufficiently large, or all tables that had more than 100,000 cells, were synchronously written to disk. So whenever you had any table generated in a Knime workflow that had some noteworthy amount of data, this would be written to disk, and this would take a long time. And we knew that this took a long time, and we wanted to optimize this. And our first shot in optimizing this was to introduce the Parquet column store in the persistence as an alternative persistence layer. And so the idea here is that instead of seriously or synchronously and sequentially writing row by row by row by row to disk, we would then write in a columnar fashion, which would allow us to access a table also in columnar fashion. So this means that you write a table with 100 columns and 100,000 cells. And if your downstream node is only interested in one particular column, it can just read this one column from disk. So with this new column store, we would get major speedups when accessing only parts of a table. So a certain range of rows or a certain number of columns. But most Knime nodes, as you might be aware of, do still iterate over the full table. And we found that iterating over a full table was still as slow as before. And so we learned from this that it's not so much the fact, or it's not so much how we persisted to disk, but that we persist to disk so often in the first place that costs us a lot of performance. So what we did next in Knime 4.0 was we introduced a least recently used cache for medium-sized tables. So what is a medium-sized table? It's basically a table that has more than a fixed number of cells. And this fixed number of cells we changed from 100,000 cells to 5,000 cells. But this medium-sized table at the same time is not too large to fit into the heap. So basically any table that fits into your Knime JVM's heap, but that is larger than 5,000 cells would be considered medium-sized and would be a candidate to be placed in that cache. And then when your upstream nodes generates data, it writes this table into this least recently used cache. And when downstream nodes access this data, they would just be able to read it from the cache without having to look look for the persisted data on disk. And that would make it a lot faster for any workflow, basically, which processed data that is not super small, but also not super large. But what we also found is by placing all these quite or potentially pretty large tables in our heap space, we would first of all, the memory footprint of Knime would consistently grow or would stay at a consistently high level, or could stay at a consistently high level depending on what data you process. And it would also put a high pressure on garbage collection. And I'll get into what this means in a second. So now with Knime 4.3, we are introducing a complete rewrite. And this graphic should really show you that it is a complete rewrite. So previously we had a package with subpackages that was called org Knime core data. And this is where pretty much all our data storage code would reside in this package or around that package. And from there, we had the old persistence layer, org Knime core data container, and we had Apache Parquet as an alternative, which we introduced in Knime 3.6. Now we have a complete rewrite. So not only is the internal data handling rewritten with this org Knime core data v2, but there's also the whole backend, the whole persistence layer is also rewritten, and it makes use of Apache Arrow. And these sentences are taken from the Wikipedia entries of Parquet and ORC and Apache Arrow. So Apache Parquet is a column-oriented data storage format of the Apache Hadoop ecosystem. So it is column-oriented, and it is about long-term storage, whereas Apache Arrow is a language-agnostic software framework for developing data analytics applications that process columnar data. So this is more of an in-memory columnar storage format. And so it is a whole different animal. And even though it shares with the old Parquet extension that it's a columnar data format, which allows us to access data in or just pieces of a table, just particular columns or a particular range of rows, it is a completely new animal for us. Also, what you notice here is that Apache Arrow not only has a persistence technology, but it's also the data it keeps in memory, it keeps in the off-heap memory region. So that is away from where the garbage collector, the Java garbage collector, has control over, which takes off this garbage collection pressure that I was talking about earlier. And there's also a completely new preference page for this columnar table backend. And the old table backend preference page, which you see here on the left side, has moved to Knime table backend default. Previously, it was just called data storage and would be a top-level element under Knime. Now it's moved here, and it has been and next to it, if you have the extension installed, you'll find the preference page for this new columnar table backend, which gives you a lot of advanced options for customizing your cache, which I'll talk about in a couple of minutes. So how can you get started with this? Right now, you have to install you have to download the nightly version of Knime Analytics platform, and keep in mind that we are pushing changes to this on a daily or even hourly basis. So there might be some issues here and there, but then on the next day it might all be good again. But yeah, so if you want to play around with it now, just download the nightly version from our download page, or wait until the full release on December 6th, and then you can install this extension as any other extension and you just have to look for a columnar table backend. And once you have this installed, you can activate it on a workflow level. So you go into your Knime Explorer, you right-click on a workflow that you want to activate this on, you press Configure, and then you get this dialog where you can select the table backend and switch it to the columnar storage. And you get this red warning message, which basically tells you, okay, this is not quite production ready. This is a labs feature. So this might be a lot faster than what you're used to with the default backend, but don't use this quite yet for your production workflows. Eventually, the goal is for this to become the new default, but we still have many improvements planned. So until that is done, this will be a labs extension. Yep, so this was our first item on today's agenda. And yeah, what I forgot to mention at the beginning, if you have questions, just write them in the chat, and Christian, who's also in this call, Christian Dietz, will be happy to collect these questions and then present them to me. And this is the first opportunity for any questions, should there be any. Christian, do we have any questions so far?
No questions so far.
Okay. All right, but now you know that you can shoot questions, and we can discuss them immediately as we go, I'm also happy to discuss any questions should they arise at the end of the talk. So let's go forward and talk about our design decisions. And now we're really getting to the details of this table backend. So one of the main motivations for doing this, or one of the main things that we wanted to do, is we wanted to keep primitive data primitive. So what does this mean? So on a 64-bit platform, which most platforms are nowadays, with more than 32 gigabytes of heap space, how large is actually a Java object? How much memory does it actually occupy? And for each Java object, you have an object header that takes up about, well, with these configurations, 16 bytes. And then you have the actual object reference, which takes up another 8 gigabytes. And then this object might hold additional fields, and then the size of the object will increase. But in the end, the total object size will be padded to a multiple of 8 bytes. So what does this mean? In Knime, a very basic type is an int cell, which is just a cell that holds an integer. And every cell in Knime currently is represented by its own object of type incel, or its own incel object. And as you can see, this incel just holds a single value, a single 4-byte int, but still it takes up 24 bytes in memory because it needs the object header and it needs this 4-byte int information, and it is then padded to a multiple of 8 bytes, so that makes it 24 bytes in memory. But the actual information that this int cell holds can be represented with 4 bytes because it's just a single int value, which just takes 4 bytes. So actually, by having this wrapped into its own object, or having this boxed into its own object, we lose, our memory footprint increases by a factor of 6. And looking at a more complex data type, let's look at local date time cell, which is as the name suggests, a data cell for local date time values. And this local date time cell has two fields, one local date time and one local time field. And when you go into these fields, which are Java classes, you can see what kind of information they hold, what kind of fields they have. And if you sum this all up, then this local date time cell has two references on two objects, has its own object header. Each of these local date time and local time fields have their own object header and have their own information. And altogether, this takes up 80 bytes in memory on 64-bit platforms, again, with more than 32 gigabyte of heap space. But again, this information can be represented by as little as two long values, which takes up 16 bytes. So again, we have a factor of 5 in the increase of our memory footprint for even this more complex, this type that might appear complex in a way you might think, okay, there's probably not as much to save here as with an int cell, but actually there is. So with this new columnar table backend, we are able to, or we no longer have each cell no longer has their own object. And this means we keep primitive data primitive, we reduce the memory footprint by a lot, and this allows us to hold more data in memory. So tables that were previously couldn't hold in memory because they were just too large might now fit into memory, which is good because the less we have to persist to disk, or the less you have to access data that you wrote to disk, the faster we will be. And also we save these object creations, and we save a lot of time for the garbage collector, who has to go over these objects again and again and again until eventually it can reclaim them. So it's good in two ways. We reduce the memory footprint, and we reduce the number of, or 3 ways even, we reduce the number of operations, and we take load off the garbage collector. Yeah. Another thing is, let's talk about garbage collection. I've touched on this quite a few times now. So you're probably familiar with what it is, but just what other consequences does it have? So the JVM heap, as you might know, is the region of memory for dynamic memory allocation of Java objects. So say you have your local date time cell or your int cell. This object will be placed in the JVM's heap. And the size of this heap you can control via the XMX parameter, which you can enter inside your Knime ini, and then depending on what you entered there, your Knime would start with less or more heap space. The garbage collector is a thread or a number of threads that iterate over this heap area, and it looks at, okay, which of these objects are no longer needed, which of these objects are no longer referenced by any other objects, and if it finds any of those, it will reclaim them, which means it will free the memory that is occupied by these objects. And as you might imagine, this costs a little bit of resources. So ideally, under normal circumstances, the aim of modern garbage collection is that this should take about 10% of your total resources. But as you might imagine, as your heap fills up with long-living objects, like these Knime tables with their cells, they can be pretty large. And if your heap fills up with them, the garbage collector becomes more and more aggressive, trying to free memory, and it goes over these same tables all the time, looking for places where it can free memory. And the more scarce the memory becomes, the more resources this garbage collector ends up taking up. And this is what we call GC pressure, or garbage collection pressure. So it is actually a bad thing to block too much memory for too long, because the garbage collector is really just efficient when it can actually collect something and doesn't have to go over the same objects all the time. So with using Apache Arrow in our backend allows us to go off heap, which means that these primitive data that we talked about on the last slide are now placed in the off heap memory region and are no longer subject to the garbage collector or garbage collection pressure. The negative of this is that any non-primitive data must be serialized. So if we're talking about something like a string cell or a row ID, which also is a thing in a Knime table, or if we talk about these local date time cells, they might hold data that has to be serialized because the off-heap region doesn't have a notion of Java objects. So everything has to be converted to byte arrays if it's not a primitive. And this is one drawback of going off heap, which is why this bullet is marked red here. Another drawback is that we're more susceptible to memory leaks because the garbage collector makes it easier for the developer not to care so much about when, or the garbage collector basically takes off the load, takes the load off the programmer to determine when they can allocate or when they can free memory. With this new table backend, Knime does this manually and explicitly, and just in general, going off heap makes you a little bit more susceptible to memory leaks. But the good things about this is that, again, we take a lot of load off garbage collection, and we have a much more controllable memory footprint. Because with it, we talked about the size of Java objects on the last slide. These 24 bytes for an in cell, these 80 bytes for a local date time cell. These are just figures that you have to compute yourselves. Java doesn't tell you about these. So you don't get to know the size of a Java object at runtime. But when you're going off heap and everything is serialized to byte arrays, you know exactly how much memory each of your or all of your data consumes. So with this new architecture, we can design, or we were able to design a cache that you can, for which you can exactly control how much memory it is allowed to use. And that is really cool because it no longer do you have this this filling up heap where you have little control over, but you can just say, okay, I want my cache to take up to 1 gigabyte of my main memory, and that's fine. Then another thing that's really cool about this is that by storing our node or any computation or any intermediate results that your nodes compute, or as a node developer that you might be using, or any external libraries, they will still place their objects in the heap region, and no longer will they have to interfere with our internal table storage for space and garbage collection resources. So previously, you might run a memory-hungry node like the duplicate checker or a sorter, and it might perform better or worse depending on how much memory you still had available and how many tables you put into the cache beforehand. Like it might have a better performance if you just started Knime freshly, and performance might have degraded if you just executed a couple of workflows and filled up the cache. Now with this, there won't be so much interference between the data storage and the node operations. So again, we get a much more controllable environment and a much more stable environment. And finally, but maybe most importantly, this storing our data off heap is a first step in enabling shared memory with other languages. So the plan is to end up in a world where our Python nodes can directly, our Python nodes can directly access the same memory as our Java nodes can, and which would make them miles faster. So some final design decisions and benefits. In order to talk about them, I quickly want to get some definitions clear. So on the top left, you have a Knime table, or just a table comprising m columns and n rows. So a single entity in this, or a single row slash row crossed with a column is a cell. Then you have a row, you have a column. And now in these columnar stores, like Apache Arrow, what you do is you split the table into chunks. So you have a chunk of data, which is really just a chunk or a piece of a column. And then you have a batch over multiple of these chunks, which is really just a batch of chunks, or also a batch of rows, which you'll see on the far right of this graphic. And with this new table backend, we're doing a lot less operations per data cell, and we moved many of these operations on a per chunk level. So where previously in the old backend, we did a lot of work for each individual data cells and a lot of expensive operations as well, a lot of instance off checks, a lot of very nested if then else case logic, a lot of class casts and so on. Now we just don't have to do this anymore because of a different design, basically. Another really cool thing about the new cache is that we no longer store the full table in memory, or we no longer have to store the full table in memory, but we're actually caching the chunks. So it's not so much an all or nothing decision. Since Knime 4.0, a table would either fully fit into your heap, or it would not fit at all. And it would either fully be placed and take up all the space that it needed, or it would not be placed in memory at all. And now we're actually able to cache individual chunks. So say you always access the same chunk in your table, then the cache will maybe just hold this particular chunk that you keep accessing, and all the rest of the table, it'll just persist to disk and it will forget about it eventually. And finally, Knime has been in the game for a long time, and the whole backend has evolved. Features have been added, and this is just kind of a spring cleaning where we say, okay, now we have the chance to start fresh with a clean and clean code base that is more maintainable long term. So we're also really excited about this because we think that with this new table backend, yeah, we'll be able to have a lot more control and a firmer grip on what's going on. Yep, so this is mostly what has changed and what our design decisions were. We went off heap with the data that we store in memory. We're reducing the overall memory footprint by keeping primitive data primitive, and we're just reducing the amount of operations that we do per data cell. That's basically the gist of it. And again, if you have any questions, I'm happy to take them now or later. So Christian, do we have any questions at this time?
No questions that I can see so far.
Okay, that's fine also. Then I'll just continue with the cache architecture and the configuration options that you have. So I've been talking a lot about caching. So I mean, you're probably familiar with this, but maybe not. So let's just get the terminology straight. So a cache is just a piece of software that holds data for you so that you can access it faster. And in this case, in the slowest, imagine you have two Knime nodes, one upstream node, which is a data source, and one downstream node, this red one, which is a data sink. And the data sink reads data from the data source. So the most expensive option, and the one that was the default in Knime 3.5 and before, is that you would just write this table to disk into a file. So the orange node just writes data into a file, and the red node reads data from that file. And as you might imagine, we can be a lot faster if we don't do this, and if we just keep the data, or if we can still do this, but if we just keep this data in memory. And so if we put a cache in between in memory, that allows us to, that allows the red node to read this data before it has been fully persisted to disk. So this is the idea of a cache. And in this new columnar table backend, we have actually a multi-layered cache. So this is just a sneak peek, but I'll get through these individual layers now one by one. So again, let's start with the very basic. If you have all caching disabled, what you see on the left is still what you get. So your data source writes data into a file, and your data sink reads data from that file. But as you can see, we have a little legend here. This writing is actually an asynchronous operation. So it happens in its own thread. And then you have also what Knime has to do internally is it is checking for duplicate row IDs, and it's also calculating domains of the individual columns. And this also happens in an asynchronous thread pool. And the size of this thread pool, you can already configure here on the right side with this yellow boxed configuration option. Yeah, and the first level, the first cache layer that this new cache consists of is just a general data cache, which will hold chunks of data. And again, let me go back a little bit. Chunks are these small parts of a column. And this general data cache just holds arbitrary chunks of arbitrary tables. And you can configure its size with this box on the bottom right. And there is some auto guessing, some smart guessing of what a reasonable default size might be. So if you click restore default, so if you just leave this the way it is and you do not uncheck this use default values box, then you will get something that takes into account the amount of heap space you allocated to Knime. It takes into account how much free memory you have available at the time you start up Knime. And it also takes into account how much memory your platform has available in theory. And we're pretty conservative about this estimate. And so we're trying to make sure that that this cache doesn't take up system resources that you might want to use for other things. Yeah, so basically it's a minimum of these three. If you assign Knime via the XMX parameter to use 4 GB of heap memory, this cache won't take up more than an additional 4 GB. So that's the first of this minimum. If you start up Knime with only 2 GB left, then this cache won't take up more than a single gigabyte because it'll assume you probably still need a little bit to work with. If your system only has 32 GB available and you gave Knime already 30, then or 28, then again this cache will start with a pretty low value because it'll notice that pretty much everything your system you already have allocated to Knime's heap area. So feel free to play with this parameter. And just bear in mind that whatever you set here, Knime might take up in addition, or Knime will probably take up in addition to what you control via the XMX parameter in your Knime ini. So if you're moving from Knime 4.2 to 4.3, you might consider reducing your XMX setting in your Knime ini and increasing this setting instead, which will give the cache more memory to play with. Okay, so far so good. So this was a very complex, or the option itself is not that complex, but there's a lot to the default value of this option. Okay, so what happens now with this cache enabled? The data is once again written asynchronously. There is there's a thread pool for checking duplicate row IDs and calculating domains. And then this data is serialized into the off-heap memory region. And from there, it's again asynchronously persisted to disk. But as long as it resides in this general data cache, your downstream read node will already be able to read that data and to work with it. So the orange node will be green, even though data has not fully been persisted to disk because this cache is in place. And only if you have a cache miss, that is, if this red node tries to access a chunk of data that is not available in the general data cache, only then you will have to read that data from disk. And only then you will have a performance decrease. Okay, so this is all well and good. And this is definitely the most memory hungry and also most important component of this overall cache architecture. But The problem with this is that if you have a really small table, say just a single cell, just a super small table that you loop over all the time. You have this loop that loops over a single, or that creates an individual table just comprising a single cell for 100,000 times. Then for each of these 100,000 small tables, you would create a file in the background. And even though you would write asynchronously to it, it would still cost you a lot of performance. So there's another cache layer in place that just blocks any small tables. So if the table that this orange node writes is just super small, then it'll just be placed inside that small table cache, and it won't even pass onwards, or it will only be passed onwards if it's ever dropped from that cache for whatever reason. And you can control the size of the small table cache, again, with these parameters. You can say, okay, I consider a table to be small if it takes up 1 megabyte of off-heap space. And I want my my small table cache to be allowed to take up 32 megabytes of off-heap memory. And again, you might see why it's so nice to, or one of the reasons that I talked about earlier with going off-heap is that we know exactly how large a table is. And the benefit you can see here, you can just say, okay, this table is 500 kilobytes in memory, so it is a small table, and we don't no longer have to guess, okay, this table has 5,000 cells, so probably it is a small table, but if these cells are super large string cells, then maybe it isn't a small table, we just don't know. Well, now we definitely know, and we can control this very accurately. Okay, so there's one last piece of the puzzle of this in this cache architecture and this hierarchy, and it is about serialization. So remember, I talked about this earlier, that when you place data in the off-heap memory region, you have to serialize it. So if you have complex data, you have to convert it, copy it into byte arrays. And this costs a little bit, obviously, and it also costs a little bit to deserialize them, to transform these byte arrays from this off-heap memory region to proper Java objects again. And these nodes that you're working with, they need proper Java objects to be able to do anything with them. So there's one cache in between that caches these Java objects. And so if you have your complex Java objects, they are placed in this complex data cache. And the serialization to the further layers of caches then happens asynchronously again. And your red downstream node can read objects from this complex data cache even before they're fully serialized. And now you might say, okay, but having this complex data cache in place means that my heap space still gets filled up with objects, because these objects that are placed in this complex data cache, they lie in the JVM heap, and that is true. But you have an object that or you have a configuration object for this, which you can set to either maximize performance or minimize memory footprint. And if you go to minimize memory footprint, which is the default setting, then your memory footprint will not suffer due to this at all, because, okay, this is really technical now, but these complex objects are then only weakly referenced in this cache, which means that the garbage collector can just collect them the first time it passes over it. So when your data is only in this cache and nobody else uses it anymore, then the garbage collector will just collect it as if it were unreferenced. Okay, so this was very technical, but just bear in mind, you have these two options. You can either maximize performance by allowing this complex data cache to actually hold some data for a little bit longer, or you might minimize memory footprint, and then this complex data cache will drop its data pretty quickly, but you won't notice any increase in memory footprint at all as a consequence of this cache being in place. Okay, there we have it. So a multi-layered architecture of 3 caches that delegate to one another and that asynchronously pass data from top to bottom, and that access data from top to bottom on cache miss. So again, your orange node writes into the first cache, this asynchronously passes the data to the next one, to the next one, to the next one, and your red node reads from the first cache. If it doesn't find data there, it goes to the next one, to the next one, to the next one. Similar to your, if you have a CPU with your L1, L2, L3 caches and what have you. Yep, so that's pretty much it. And there will be additional options probably down the road to configure this. But for now, bear in mind, all of these options are really for advanced users. So if you're uncertain about them, probably just leave them the way they are. Okay, and that was that. That was about the cache architecture. Christian, do we have any questions?
Yes, we have one question. So will row keys be stored in this way too? Or will row keys still use the existing deduplication with disk cache they currently use? So basically the question is if row keys are also part of this whole cache machinery, or if for deduplication we will still use the chunking and on this serialization thingy we use today.
Okay, so maybe I'll start answering this question, and Christian, if you have anything to add, just go ahead. So the row keys are just right now treated as regular strings. So yes, they are part of this caching architecture. They will be handled similarly, but if you have under the hood, they are still, up until they go into the off-heap memory region, they are still regular string objects. So that means they will still be placed in this complex data cache. They will still, if you have this string deduplication setting in your Knime ini, they will still benefit from that. And yes, so the answer is, the short answer is yes. They're, as any other data cell, they are part, or they will be placed off heap. They will benefit from this. But
maybe,
okay.
Sorry, maybe to add to that, at the moment for the deduplication, we still use the existing mechanism, and we have in parallel a system which writes the row keys to disk and loads them to disk again, which is independent from this caching architecture. However, this is the first thing, and one of the reasons it's still in labs. The first thing we do, we will actually get rid of the current deduplication mechanism and use the arrow cache in the backend as well.
Yep. Yes, so this deduplication, this check for duplicate row keys, is still an old code path. And as Christian mentioned, it is actually, I think, the first performance improvement we want to tackle after the release. And when this goes out of labs at the latest, this will have made it in. But the data itself will go through that cache once deduplicated. Also, another sneak peek or another thing worth mentioning is that eventually we might also provide you with an API where you don't have to create your row keys manually all the time, but where row keys are just generated automatically. And in the backend, they will then no longer be strings. So as you might imagine, if you have your Knime table with your row keys, which are string objects, and then a single column of integers, it's actually the row keys that take up most of your memory, and also that take up most of your CPU cycles. And down the road, there will be something where this performance degradation due to row keys will be a thing of the past, should you choose to use them in your node development. Yep. Anything else? Other questions? Christian?
No other questions yet. No.
All right. So let's then go onward and talk about this new table API. So this table API is something that we've just very recently fiddled around with. So it's still subject to change, but we're getting closer and closer to where we want it to be. So this is a minimal data source that just generates a single table with row keys and 1,000 integer values with the old API. So you generate your data table spec. From your execution context, you create a new data container, and then you have your loop, you create row keys, you create your data cell, you create your data row, and then you add that data row to your table. And in the end, you close your container and you get the table from the container and pass it onward to downstream nodes. Now with the new API, this is slightly changed. So I'll gray out what is similar. And with this new API, it currently looks like this. You still have your container, but it's now no longer called buffer data container. This is actually a row container. On your container, you create a row write cursor. And then you loop over, once again, you have your loop. You get your row, you create a row key, you set the row key in the row, you get your int write value, and you set an int into that. And as you might, by just comparing the two, they're about equal in length. They're about equal in style, I would say. I mean, if you transition your node from the former to the latter, there's not so much work you have to do. But as you can already see, there are a lot less object creations here. So with the old API, you would create a row key object. You would create a row key object. That row key object holds a string object inside. You create your data cell object or your in cell object, and you create your default row object. And with this new API, you really just have the row key as a newly created object. Everything else is reusable. So with this int write value, for instance, that you get in the third line with content from the top, it's reused. So whenever you push your cursor forward, then this object is reused. You don't have to create it anew every time. And you might have noticed where previously you just created your container and then you put pushed your data in. Now you still do this, but you have this cursor layer in between, and this already hints at that there might be multiple cursors in the future. So this allows us eventually to have multiple write cursors potentially, where you can then push data or where you can then create data in multiple threads for even more speedups. And as I also touched on earlier, the thing that really bugs me personally about this, about the code on the bottom, is that we still have to create the string for each individual row. So eventually we want to get somewhere where you don't have to do this if you don't want to, and you can just let Knime do your row ID management and not create these strings for every row. And again, this is subject to change, so this is not quite set in stone, but we're super interested in getting your feedback. And this is true for everything I've been talking about today. So if you have feedback, please share it with us. We value it highly and we definitely listen. Okay, this was the data source, data sync, pretty similar. Again, this is for the old API. You have this is how you should use the old API. You have your closable row iterator that you get from your buffer data table. And then while you can still iterate over it, you get the next data row, you get the data cell, then you cast the cell to an int value, and you get the actual primitive int out of that value. And again, you can see for just storing a primitive int, we're handling super many objects here. And we also have to cast here. Yeah. And with the new API, this gets a bit leaner. Again, we're working with cursors, and the difference is between an iterator and a cursor is just that in a cursor, the objects that the cursor gives you are reused. So this row read that you see here in the third line from the top is reused whenever you forward the cursor. So the cursor is really just a window that slides over the data, whereas previously in the old API, the iterator is really new object, new object, new object, new object. And here is just a window over your table that is a lot more lightweight, I would say. But other than that, it's very similar, just that you don't have the notion of data cells anymore. You just don't, because you, as mentioned previously, we don't create individual data cell objects per cell. So we just get the value. You're able to get the value directly. And again, this is subject to change, and we're eager to get feedback. Yep, so this about sums it up. So this was a peek at the new table API that you will be able to work with come Knime 4.3. Christian, do we have any questions?
Yep, there are two questions. The first question is about the maximize performance option in the cache. So if you turn on the maximize performance, this will then actually cause additional garbage collection overhead because there's so much stuff in the main memory, right? So how does this relate to the principle that we don't want to have GC pressure?
Okay, so yeah, maximize performance. So it's really a double-edged sword. In the old cache, so let me go back even further. In the old cache that we introduced with Knime 4.0, this LRU cache, what it actually looks like, as I mentioned, it is an all or nothing cache. So it keeps full tables in memory or no table in memory. So if you have your Knime table, either it is medium-sized and it fits into there, and if the next medium-sized table comes along, it might kick your whole old table out, or these two might still be able to fit inside that cache alongside each other. But it's always an all or nothing decision. But it's obviously super dangerous to have these large objects there in your heap space, and then your sorter node comes along, requires a lot of memory, and then you get your out of memory error. So to prevent this, what this old cache actually does is it holds these tables softly referenced, which means that Java guarantees for you that before you're running out of memory, before your JVM runs out of memory, these tables will be dropped from the memory. So they're actually not that they block your heap area, and they take up memory, but only as long as memory is not becoming super critical. Before memory is running out, the cache will release these resources. And so it's similar with this new option. Maximize performance basically means keep these chunks of data softly referenced in the cache, whereas minimize memory footprint means keep these chunks of data weakly referenced, which again means that the garbage collector discards them the moment it goes over them and notices that nobody else uses them anymore. And so this is just the difference, in technical terms, what it means. There's also another mechanism in place that will, even though if you set this to maximize performance and these tables or these chunks of data are softly referenced, what it will actually do is if your heap space consumption reaches a critical point, about 65%, it will just release them, because we just don't want garbage collection pressure to become too high. Okay, so these are the details, but the actual question is, how does this relate to GC pressure? Will you still experience GC pressure with this setting on? And the answer to this is maybe, but probably not as often, because this cache really only holds complex data. This cache really doesn't hold the primitives anymore, and doesn't hold these int cells anymore, and these double cells and these long cells. So even if you set this to maximize performance, you will only experience heap pressure, garbage collection pressure when you're working with a lot more data than previously. But the reason why the default setting here is minimize memory footprint is exactly that we want to reduce memory garbage collection pressure, and we want to be careful about this. And that's why setting this to maximize performance is not the default. Okay, that was a long story. Christian, do you have anything to add?
Yes, more questions. So we have another one, some interesting ones. The first one would be, if the read-write objects are reused, is there a method or benefit to getting them on the first read-write of the table in the node and then just moving the cursor? Or does this happen effectively anyway? Perhaps it does really.
Yes, Christian, do you want to take this one?
Yeah, I can answer that. So in the original design, we actually wanted to do that, to get the read and write values once out of the loop and then reuse them. However, there are situations where we can't guarantee that we always have the same object. So we might even have different objects returned by the forward. Then we benchmarked it, and this additional method call in the loop is not really causing any harm because it's usually optimized away by the JIT anyways. So that should be fine. I hope this answers the question.
Yeah, so basically, I just redid my slides and updated this, and before we had it in as suggested or hinted at in the question, and now we have it like this. So as mentioned earlier, this is subject to change, but we are careful with changes like these because that's essentially what we want to prevent, these expensive operations per cell. But in this case, benchmarking showed that this is actually not costing us.
The next question would be, is there the capability or plan to add the capability for moving the cursor more than one forward at a time, which is basically random access to tables? Marc, should I, or do you want to answer this one?
Well, I think you have more to say, so let me start, and then you can say you can add things on top. So my answer to this would be probably not with this cursor API, because the cursor is really similar to an iterator in the way you use it. But we do have plans to eventually, I mean, under the hood, this is a columnar data storage with Apache Arrow. And this cursor really masks that it's actually a columnar access below that. So what we want to, eventually we want to expose a columnar API to the user, which allows you to have a lot more direct access on data, maybe even on a chunk level, where you can get, if you know what you're doing, can really optimize this for performance and just have direct access on the data. Christian, anything to add?
And actually, you can already have this quasi-random access today if you use the table filter API on a row cursor. You can already select the row where you want to start reading, and in the case of column store or columnar tables, the new ones, we won't iterate over all the data in the nth column before the nth row, and we will directly jump to the nth row. So that's quasi-random access. So we could expose this API in a more convenient way in the future. But as Marc says, we are careful with these changes because we don't want to guarantee something now which harms performance tomorrow, for example, in case of distributed systems. And maybe we want to reuse the same API there as well.
Yes. But with the Parquet backend, we added this iterator with filter operation, and we also now have a cursor with filter, and this is this table filter that Christian just talked about. Okay.
Yeah. There's another question which I will quickly answer, and then there's another one for you, Marc. So there is a question: will new data types now need to have readers and writers implemented? The question is, if you want. So if you don't implement readers and writers, we have a fallback mechanism which basically offers a data cell reader writer. You won't notice that if you use the new Columnar framework in the backend in the legacy mode. If you want to use the new API, then you can actually ask for this data cell write value and the data cell read value. However, then you will still have the data cell overhead associated with the new API as well. So therefore, we offer an extension point where you can actually add your own write and read value for your own data type optionally. Okay, now the question for you, Marc. Could you maybe quickly repeat the motivation behind having a write value object?
Yes. Oops, I'm not even sure. Yeah. So this write value. Yes. So again, this cursor, whereas previously you would create a single data cell for every integer that you store in your table. Now you have your int write value where you put your integer values inside. And the difference here is that Here you create a new object for every int. And down here, this int write value that you get from your row write is actually the same object that is being reused. So you don't, this int write value as your cursor, which is really just a window on your to be written data, as that cursor moves forward, this int write value will basically move forward with the cursor. And when you put your int inside, it will place that primitive int at that position. And when your cursor goes forward, this int write value will go forward with it. So you don't have an extra object allocation. But I mean, you still have to somehow say, okay, this at this particular column 0 in this case, we're writing ints. And that's why you still need an int write value. But no longer do you need an int self at every place. Did that answer the question? Well, I'm not getting any feedback, so I just hope this answered the question.
Okay, and we are already 1 minute over time, but there's one last question I would like to answer. How many nodes do already make use of this API to achieve the current speed up?
The answer is, Christian, do you want to go ahead?
Yeah, actually, none of the nodes is currently using this new API. They are all, so that the benchmarks we have shown are all operate on the old API, writing into the new backend, so in full legacy mode. So we expect some more speed up when we actually also change nodes over to the new API.
Yes, and this is a nice overhead or a nice, this takes us to the Outlook. It's a nice transition because that's exactly what I wanted to talk about here is, so currently this feature is in a fully usable lab state. You can just configure your workflows to use this new backend instead of the old one. If your node doesn't support the new API, if there's a data type that we haven't explicitly supported or that you haven't done everything you can to work with this new backend, it will work through a transition layer. So that means in the backend, it will still write everything in your off-heap region, but this transition layer will then generate data cells, for instance, for your iterator to work with. So this transition layer has some overhead, but already, as you saw from the first slide in the talk, we get considerable speedups with this. But we expect more speedups once nodes actually transition to fully benefit from this. And these are exactly the next steps. So first, we want additional improvements to become production ready and squeeze out more performance. And the first one of these squeeze out more performance issues we already touched on, which is this duplicate checking for our row IDs, that we also want to move this to the new backend. We also want to make use of this new backend in streaming. We think we can gain a lot from this. And then also we want to rewrite frequently used nodes to use this API, the new API, and get even faster. And only then we will also look into other places where we can save some more time and improve performance further. So these are the next steps. But again, this can be used with any node that uses the old API. The new API is really something optional for getting even faster with this. Yeah, that was everything that I have for today. We're already a couple minutes over time, so I'll leave you to join the other talks. Christian, do you have any final words?
Final words is an answer to the final question, I guess. Is there a plan for something similar to column rearranger, etc.? Absolutely, yes. We are on that. That's part of the upcoming changes.
That's also belongs into this category of squeeze out more performance gains. All right, then thank you very much for joining today. If you have further questions, feel free to shoot us an email or let us know in the forum. There has been a blog post on this new columnar table backend, and in this blog post, there's also a link to a forum post where you can also discuss this feature and share with us your feedback. And yeah, we're super excited to having worked on this and to continue to work on this. And we're also super excited to get your feedback. So thanks for joining, and talk to you next time.